Utilizing wide area surveillance assets, based on the scripting scenario mentioned earlier, airborne cameras provided imagery of regions and entities of interest, and conceptually, the image data was processed to form and maintain tracks on entities of interest. Then processing was performed so that the track data was classified to provide entity descriptions which would support an intelligence analyst. The GPS data was considered as a proxy for track data based on imagery from the camera systems. Data association was trivial for GPS data, but is typically complex for detections arising from video data. While video data may contain attribute information such as color of vehicle / clothing, this information is absent in the GPS data. The trial started around noon on a clear sunny day and ended just over 1.5 hours later. There were 6 GPS tracks recorded, henceforth denoted as A, B, all the way to F. To assist the analyst to interpret the entity data, the entity motion was classified into one of the following: 1. Stopped, 2. Walking, and 3. Using motorized transport. Figure 1. Speed recorded by each entity per minute interval. Figure 2. Plots of meetings between any two entities. From Figure 1, all entities except A and B have taken some form of motorized transport. However, there were some problems with the data, given that no car is believed to have traveled over 80 kilometers an hour. Even far less likely that it would be over 200 kilometers an hour. As some data points for track F indicated, the plots were maximally bound to that speed. The reason for this is not precisely known, but it could be that the GPS signal bounced off of the buildings nearby. Interactions between individuals are either directly or indirectly observed. These may be from individuals seen in the same location at the same time, or individuals linked by a sequence of related activities. Entities have certain attributes, e.g., ID, position, associated car or train, linking them to other entities. Determining the presence of entity interactions could be considered merely a subset of a full set or list of possible events. However, in ABI, social ties and networks are crucial. It could be argued they should be emphasized. There are 2 types of descriptions an entity could be categorized under: their events or tasks carried out and their social interactions. These are now described by classifying the pairwise entity interactions into one of the following: 1. Crossed paths, 2. Met each other, 3. Traveled together, and 4. We're not close. To determine whether an interaction between 2 entities took place, 3 key measurements were considered: the distance between them, the duration of a suspected interaction, and the entity's velocities at that time. Using the MET rule, the likelihood of meetings occurring can be derived as shown in Figure 2. A, B, and C met at around 35 minutes after the exercise started for about 10 minutes, and F met for about 5 minutes around the 45-minute mark. D also then meets up with F and a short time later, and on a separate occasion with E. The observed interactions identify 2 distinct groups emerge, namely A, B, C, and D, E, F. Social Network Analysis, SNA. Social network analysis represents relationships between social entities, events, locations, and other objects in the system of interest as a network. Entities are represented as nodes, and edges represent relationships between the entities, such as kinship relations, communication events, place of birth, and other persistent or ephemeral relations of interest. SNA combines social theory, mathematical, statistical and graphic theoretic analysis, and visualization. Borg, 2013, Scott, 2012, and Wasserman, 1994. And an analyst can make assessments about individuals and various aspects of the network that may not be immediately obvious, like who is the leader, who is most likely to take over if the leader is removed, who else is in position of influence, what gives people influence in this network, who is likely to have access to useful information, how difficult would it be to disrupt this network, and even are there parts of this network that cannot be seen. The entity interactions identified can then be converted into a network representation that can potentially be analyzed using SNA methods. 3.4 Geospatial Events. This section describes the recognition of geospatial events derived from the combination of navigation data with a geospatial database and their potential use in higher-level data fusion processing. Events such as entering a shop or following a particular street can be used to summarize the actor's journey in a manner that can be understood by a human operator or algorithms that look for correlations between the motions of actors in a group. Such a summary can also be interpreted as a series of state transitions, allowing behavior to be represented as a matrix indexed by the current state versus the next state. Given an entity's location, this approach permits an individual's behavior to be predicted by choosing the highest probability state transition. It also allows anomalous behavior to be detected, either in the context of the entire population or relative to the actor's normal behavior. Geospatial Database. The Community Project Database OpenStreetMap OSM, OpenStreetMap 2012, could also be used in this work. It provides free geospatial data to anyone. Data are contributed by participating users and can be used for a multitude of applications. In addition to mapped imagery, the service also allows access to the underlying database, which includes features such as streets, buildings, political and geographical boundaries, rivers, shops, and amenities, including park benches and ATMs. Given the crowd-sourced nature of this service, coverage of the database is variable, somewhat inconsistent, and changes over time. However, it is valuable for exploring the potential for translating navigational data into geospatial events. OSM data could be stored using a number of different data structures, including a list of nodes and their corresponding locations, a list of ways with their corresponding sequence of nodes and descriptive attributes, and a list of entities such as amenities with locations and descriptions. Associating track data with objects in a geospatial database. OSM data could be stored using a number of different data structures, including a list of nodes and their corresponding locations, a list of ways with their corresponding sequence of nodes and descriptive attributes, and a list of entities such as amenities with locations and descriptions. Buildings and streets could be coded using ways. In the case of streets, the sequence of nodes corresponding to the middle of the road at location where there are intersections or changes in direction. For a building, the sequence of nodes corresponding to the building's outline. Most streets have names, although roundabouts and many linking roads are not named. Buildings may or may not have names, and also, in this instance, the track data does not include height, which would not give the precise location. Where a building contains a shop, the building may take on the name of the shop, or it may be necessary to search a list of entities to find those that fall within the building of interest. Where more than one shop exists within a building, the one of interest may be the one closest to the navigation data point under test. OSM data could be parsed to MATLAB Philippidis 2012 to find if the navigation data point was associated with a street. A rectangle was generated for each adjacent pair of nodes in its way. This rectangle had a length that exceeded the length of the road segment so that the navigation data would be associated with the street even if it passed through an adjacent intersection, and a width sufficient to capture any adjacent footpath. Some footpaths are listed explicitly in the database, but these were not. A test was then made to see if the data point fell within the resulting rectangle. Event processing. A collection of event sequences can be used to form a model of normal behavior. Such a model may be used for prediction and anomaly detection. A simple approach is to generate a matrix that represents the transitions from one event to another. This matrix formed with rows representing the current event and columns the next event. The entries represent the probability of the state transition, i.e. it is a Markov chain, so that the prior distribution is uniform and has a high level of uncertainty. The matrix is initially filled with ones. 4. Jalapeno trial. Conducted on late November and early December of 2014, this trial shared many of the same features as Pimento, but there were also new aspects which are worth mentioning. In this trial, video data was used in the analysis. 2. Artificial social media data were also created by participants and used to assist analysis. 3. While the trial scenario was the same as that in Pimento, the ground activities were subtly different. Instead of having two distinct groups doing sets of activities, there was now one group carrying out all activities involving the transfer and movement of a package which contained a GPS device. 4.1 Ground activities. As in Pimento, this team consisted of DST group volunteers who set out to carry a set of prescribed activities. Unlike the Pimento trial, there was one group instead of two, working together and cohesively. Here, the task was to coordinate a public nuisance event in the form of a protest. The data collection for this trial is similar to Pimento. However, in this exercise, there was also the injection of artificial social media information as another source of data which could be exploited. One of the objectives of this exercise was to determine which GPS track is inside the package and understand its movements. 4.2 Data analysis. Just like in Pimento, the GPS tracks are analyzed so that the interactions among them may be detected. A log with the potential interactions with latitude and longitude values is generated. These interactions are then cross-checked with the video data for verification. There were some moments where the video data could not determine whether there was an interaction or not. As an example, there was an instance where the camera's view was obscured. In this situation, social media data can be examined with a simple keyword search to detect not only potential interactions, but also to provide some context on the reason for the interaction. The importance for fusing hard and soft information cannot be understated. Linus and Scrifani write, quote, "The experiences of Iraq and Afghanistan have also shown that inputs and supporting information such as contextual information, either real-time or in static databases, of a textual linguistic type have proven helpful, if not crucial, toward yielding improved intelligence analysis capabilities. This type of information has come to be called soft, to distinguish it from hard, physics-based," unquote. Data provided by the usual reporter of ISR sensing devices across the electromagnetic spectrum, Linus 2014. Finally, recall that the parcel in question contained a GPS unit. If one assumes that this parcel was handled by most of the other entities, then it would be expected to be the most connected entity. Displaying all the interactions in the form of a social network shows that entity B is the parcel. Figure 3. Figure 3. Graphical representation of entities and their interactions. 5. Conclusion. This paper provided an overview of recent ABI trials. In Pimento, the aim was to develop and formulate concepts that could be useful in understanding ABI. In Jalapeno, these concepts remained with the aim there to combine data from different sources to obtain both kinematic information, what, and contextual, why data. The integration of numerical with qualitative data continues to be an ongoing and challenging problem. References: EAE 2013, Watching Your Actions, Finding the Right Hay in a Haystack, EAE Systems Magazine. Borgatti, S.P., Everett, M.G., and Johnson, J.C., 2013, Analyzing Social Networks, Sage Publications. Flipidis, 1, 2012, OpenStreetMap Functions. Lash, T., 2013, Uses of Motion Imagery in Activity-Based Intelligence, Proc of SPIE 8740 1-7. Linus J. and Scrofani J. 2014, Foundational Technologies for Activity-Based Intelligence, a review of the literature, Naval Postgrad School Tech Report NPS EC 14001. Miller G. 2013, Activity-Based Intelligence Using Metadata to Map Adversary Networks, Defense News C41 or ISR Digital Edition. Moreland M. Duckham M. Keeley A. and Legg J. 2015, Basin Path Estimation Using the Spatial Attributes of a Road Network, Proc ICASSP 2015. OPSEC Support Staff 1996, Intelligent Threat Handbook, BIANE Publications, Co. Chapter 2. OpenStreetMap 2012. Phillips M. 2012, A Brief Overview of ABI and Human Domain Analytics, Trajectory Magazine, NDA, case number 12-463, September 28, 2012. Scott J. 2012, Social Network Analysis, Sage Publications. Wasserman S. and Faust K. 1994, Social Network Analysis, Methods and Applications, Cambridge University Press.